So what we're going to do today then is look into free fall, freely falling bodies. The problem I gave you, which turned out to be, the problem I gave you, which turned out to be an answer of 32 meters, was if you throw a rock upward with an initial velocity of 25 meters per second, if you catch it at the same height, how high did it go? Does it matter where you catch it? Not really. All we care about is how high did it go. Okay, so how do we find that answer? Well, again, I refer you to lab number 6. In lab number 6, there is a discussion. Namely, when you take an object and you throw it up into the air, or if you take an object and drop it, then the only force acting on that body in the absence of air resistance is going to be gravity. The weight of the object is pulling it downward. So in the absence of air resistance, there's only one force acting on it. The next step then is if we apply Newton's second law. With Newton's second law, since the net force equals mass times acceleration, if that means the force of gravity is equal to the mass times the object's acceleration. Now, force is gravity. The force is gravity caused by the Earth pulling down. It turns out all freely falling objects, again, in the absence of air resistance, have a constant acceleration. I refer you to lab number 6 when I actually dropped 2 or 3 different bodies and actually measured the acceleration on each one. Turns out it's constant. Now, why is that? Because, let me back up a little. And by the way, what is that constant? That constant free fall acceleration, which I write a sub g, is equal to 9.8 meters per second in the downward direction. Notice I don't put a sign in it yet. It could be positive 9.8 meters per second squared. It could be negative 9.8 meters per second squared. It depends upon how I set up my particular problem. But we do know that the magnitude is 9.8 meters per second squared, and the direction is downward toward the center of the Earth. Now, a little bit of an aside, because one of the questions I asked is, on the question I asked earlier, what is the value of gravity? A number of you said 9.8 newtons, and that doesn't make sense. The reason why it doesn't make sense is this. If by Newton's second law we see that F of g is equal to m times a sub g, gravity causes a mass to fall with an acceleration due to gravity. What happens if I have an object that's twice as massive? Does it accelerate with twice as much acceleration or half the acceleration? What does it do? The acceleration stays the same, so what has to change then? The force. The force has to change. So if I double the mass, what happens to the force? Nope. Look at the equation. If I double the mass and the acceleration is constant, then the force has to double as well. I could write this then that F sub g over A sub g, oh, I'm sorry, that's wrong. Let me see if I can control Z it. No, I can't. Okay. I can write this as F sub g divided by m must equal A sub g. There we go. That makes a little bit more sense, doesn't it? And from a physical standpoint, it makes sense. If I double the mass of an object, then the Earth is going to pull with twice as much force. Now you think, okay, twice as much force, I should get twice as much acceleration. Except, if I've doubled the mass, isn't that going to cancel it out? From a physical standpoint, the Earth is going to pull with a bigger force, but the mass is going to have a greater resistance to the change, in motion. That's Newton's first law. The more mass of an object has, the more inertia it has, the more resistance to change in motion. So they balance out, they cancel each other out. The question here.
In the first example, you put weight equals mg.
Correct.
Is it ag?
It's the same thing. It's the same thing. I'm changing the style. I'm changing it so that I don't think it's mass times gravity. I think of it as mass times an acceleration. Because according to the second law, mass times acceleration is the result of a net force. I just happen to subscript the acceleration with g to say that the acceleration that is caused by gravity is 9.8 meters per second squared. It's simply a stylistic difference, that's all. Right. If you look in the textbooks or the lab books, and if it says m times g, it's the same thing as the way I write it as m times a sub g. Okay? All right. I'm just trying to keep reminding you that g is not gravity. Okay. Now, a sub g, in fact, there it is. A sub g, also g, is an acceleration, not a force. Weight is not mass times gravity. Weight is mass times the free fall acceleration. This is my little reminder over and over and over again. Okay? All right, so what are we going to do with it? Let's take that problem I was talking about, namely, toss a rock up into the air. How high does it go? Let's make a table of knowns and unknowns. Well, we know that if the object is under the influence of gravity only, then it will have a constant acceleration. Thus, we solve it the same way as we solved from homework number 5, constant acceleration problems. We make a table with the 5 variables, and we use the 4 equations. Our table of variables, if we let up be positive, and that's another thing, is we have to establish a direction. If we let up be positive, then the initial velocity of the stone is going to be positive 25 meters per second. The time, we don't know how long it takes to get to the maximum height. That's what we're interested in when it gets to the maximum height. We don't know how high it is, so we don't know what delta y is. We don't know what the final velocity is. We're not given it in the problem. But we do know that the acceleration is going to be downward at 9.8 meters per second squared. If we let up be positive, then a sub g is going to be a negative number. All good so far? Okay. Now, when we look at this, we see we've got 5 variables. We know 2 of them. In order to solve our table, we need to have 3 of them. So now we got to look at what's physically happening. When we toss the ball up into the air, when it gets to its maximum height, do we know any of those numbers? Yes? The final velocity is going to be 0. It's going to be momentarily 0 at that time. Correct. So our physical concept is we're looking at a constant acceleration motion, which means we can apply the 4 equations. Now, these are the exact same equations you used on Wednesday that I introduced on Wednesday, with two changes. The acceleration has now been replaced with a sub g, and the change in position delta x has been replaced with delta y to reflect the vertical. Okay? Sometimes you may have seen it written, let's say, for example, this second equation here, delta y equals v0t plus 1/2 a sub g t squared. You may have seen it written as minus 1/2 a sub g t squared. I don't necessarily like that from a stylistic standpoint. The reason being that we don't have to have down be negative every time. I could give you an example. If I'm standing on a bridge and I drop a stone and it takes so long to hit the bottom, how high is the bridge? Okay? Since the velocity is downward, the acceleration is downward, why don't I just set down be positive? The equations will still work, won't they? Okay. So I will put my positive and negative for my value, my positive and negative, I'll put those into the values, not into the equations. Okay? All right, so let's take a look at that table again. We look at the table and we see that at the throwing point, the velocity upward is 25 meters per second. At the maximum height, the velocity is 0. We know the acceleration, therefore we now know 3 of the 5 variables. Therefore, we need the equation with v0, v, and a sub g that solves for delta y, and that gives us v squared equals v0 squared plus 2a sub g delta y. We solve using the algebra. I know you're really tempted to put the numbers in right here right away. Please don't. Solve it with the algebra first. That way, if you make an algebra error, I can help you with it. If you make an arithmetic error, I can't tell if it's an arithmetic error or an algebra error. Then you plug in the numbers and you come up with a height of 32 meters. Oh, one more detail, and I will make this announcement in every class, that in the upcoming test, should answers come out written, that is to say, not multiple choice, but say answering questions and stuff, if you do not have the proper number of significant figures, and if you do not have the units, you will be incorrect. Okay? Everything makes sense there? I don't care if you got the right number. If you don't give me the units, it's wrong. Okay, so get used to using units in your calculations. Let's try another problem. Let's see if you guys can work on this one a bit. Model rocketry problem. Rocket starts from rest on the launch pad. Done under the boost phase, it accelerates upward at 15.5 meters per second squared for 2.5 seconds. Then the engine goes out. The rocket continues to move upward in the absence of air resistance. My question for you is, what is the maximum height of the rocket, and how fast does the rocket go just before it hits the ground? So let's see if you can work on those, right? Get to it, please. And the key behind solving the problem is we have to recognize what the rocket is doing. Specifically this. Drawing a picture goes a long way. Now there's a couple of ways you can draw this picture. For example, you could do a velocity versus time graph. If you do velocity versus time graph, then the graph looks like this. So there's the velocity, there's the time. We see we're going to have an initial acceleration, which is going to give us this velocity at this point here over a period of 2.5 seconds. Then what happens to the rocket? It's going to start to coast, or not coast, but it's going to accelerate, but in the opposite direction. It's going to slow down, which means you're going to get a slope that looks like this. At that point right there, when the velocity is 0, where is the rocket? Where is the rocket at that point? It's at the maximum height, because here is delta y1, and here is delta y2. Then when it comes back down, it will increase its speed as it comes back down until it makes impact with the ground. At this time, this distance right here, this delta y right there, must be equal to this delta y right there, isn't it? Okay, now there's another way of doing this. So let me draw another picture. Here's the way the other picture works. First we're going to draw, First we're going to draw the rocket. So there's the rocket right here. And it's got an initial velocity, it has an initial velocity of 0. And what's going to happen is it's going to launch upward to a certain height. Now this height right here is going to be delta y1, because that's the distance it's going to travel as it goes upward. While it's going up, it's going to have an acceleration in the upward direction, which I will call A. Oh, by the way, delta y1, is that a vector? Does that have direction? Which way is the rocket going? Up, so therefore it is a vector. It does have direction. You're going upward in this case. Okay, then when it gets to that point, it's going to have a velocity at this point, which I will call v1 in the upward direction. So far, so good, right? Then the engine goes out. When the engine shuts off, the rocket continues in the upward direction until it reaches this maximum height. Now I'm offsetting it a little bit. It's not ballistic. It's just up. Well, it is ballistic, but it's up and down, not off to the side. But I'm offsetting the height so we can see it. So then it's going to go up that distance, delta y2. While it's going up, the engine is out. The only force acting on the rocket as it goes up is gravity, and so therefore we're going to have an acceleration downward, a sub g, which is causing it to slow down as it goes up. And then the last part is when it comes back down, it's going to come back down and hit the ground at this point right here, and then it's going to have some kind of final velocity, which I'll call vf, when it makes impact with the ground. All that makes sense there, guys? Now from here, we get to build our tables. We get to build our table of variables. We need 2 sets of tables. The reason being is even though we have constant acceleration in both cases, they're different accelerations. So let's take a look at what those tables are going to look like. All right, the first table, excuse me a moment, there we go. So the table of variables, if we let up be positive, under the boost phase, we're going to have an initial velocity of 0. We're going to have an acceleration of 15.5 meters per second squared, and we're going to do this over a time of 2.5 seconds. We have two variables we do not know. We do not know the final velocity, which we're going to call v1, and we do not know the height, delta y, which we're going to call delta y1. Now let's go ahead and make the table of variables for the next phase. The table of variables for the next phase, the initial velocity. Well, the initial velocity was 0 on the launch. The initial velocity on the ballistic phase, we don't know. But we do know that whatever the final velocity was in the boost phase is going to be the initial velocity of the final phase. So I can go ahead and say that v0 is equal to v1. We know the acceleration, but we don't know the height. We don't know how high it's going to go. The acceleration is going to be negative 9.8 meters per second squared because we let up be positive, and as you saw in the diagram, the acceleration arrow was pointing down. And then we don't know how long it takes to get to that maximum height. One more thing we don't know, or one more thing we do know. Okay? We do know that at the maximum height, the final velocity of the rocket is going to be 0. So what we're looking at is the motion from the engine burnout, engine cutout to the maximum height. Great. Now, how many variables do we know in the first phase? 3, which means we can fill the table using our 4 equations. How many variables do we know or are we given in the second phase? We only know 2, but there is a connection. A piece of data from the first phase does carry over into the second phase, so we'll be able to find 3 and then again finish the table. Now, under the boost phase, we have constant acceleration, so therefore we're going to use our constant acceleration equations. Our known variables are v0, a, and t. We want delta y. So we use delta y equals v0t plus 1/2 at squared. Since v0 is 0, it just becomes 1/2 at squared, which gives us a height of 48.4 meters. Anybody get that? Okay, good. A number of you did. Now, the next step, though, is we need to find the velocity. We need to finish the table out, because the final velocity from this phase is the initial velocity in the next phase. So we need the equation with v0at and the final velocity, which is just v1 equals v0 plus at. v0 was 0, so it's just a times t. 38.8 meters per second is now our initial velocity for the next phase. So as you can see, all we're doing is, once we recognize that it's a constant acceleration motion, it's just a matter of filling the tables. Okay, let's keep going. On the boost phase, we know that only gravity is working on it, so therefore it's free fall. So we know the final velocity is 0, we know the initial velocity from the previous phase, and we know the acceleration. To find the height, we need the equation which has delta y, v0, v, and a sub g. And that gives us, of course, that equation, v squared equals v1 squared plus 2a sub g times delta y2. We're looking for what? What variable are we looking for? Delta y. We're looking for delta y. So we got to do a little algebra. Hint, hint. Do the algebra first. Makes it easier for me to help you if you make a mistake along the way. We do the algebra and we come up delta y2 equals v squared minus v0 squared divided by 2a sub g. And now we get to put in the numbers and come up with 76.8 meters. Anybody get to that point? Okay. Now, we know from the drawing then that delta y1 is the height under the boost phase, the height gained under the boost phase. Delta y2 is the height gained under the ballistic phase. So all I've got to do is add those two heights together to come up with 125 meters. Does it make sense that a rocket is going to end up around about 450 feet? A little model rocket could get up to about 450 feet. Yeah, it makes sense. So we're all good in that. Okay, now the next part. How do we find the velocity coming back? How do we find the velocity coming down? We need another table of variables, don't we? This time the table of variables is going to have to include this final velocity here. So what do we know? Are there any points along the ballistic motion? Because we know that the acceleration, we know, let's try it again. We know the acceleration. We need to find two more pieces of information in order to solve the problem. Well, the two other pieces of information we can solve the problem is we can use this point right here. Do we know the velocity at that point? 0. Do we know what the change in the y is going to be from that point? What is it going to be? Not 125. No, it's close, but it's not 125. Which way is the rocket going? Downward. So the change in the height for the rocket is negative 125 meters. We got a negative 125 meters for the change in height. We have negative 9.8 meters per second squared for the acceleration. The acceleration and the change in height are in the same direction, so therefore the velocity is going to end up going up, or rather, the speed is going to go up. And the initial velocity, as we can see at this point, is going to be 0. We can also use this point right here. Do we know the velocity at that point? Yes, we do. The velocity v1. We've got that. That's the 38.8 meters per second upward. Do we know the change in the height from that point? Yes, we do. It's the delta y1, the 48 meters. So we could choose either one of those 2 points to give us the information we need to finish up the problem. You following along? Okay. Now, having said that, let's go ahead and use the top point, the point where the velocity is 0. Then we know delta y, we know v0, and we know a sub g. We're trying to find v sub f, the final velocity. So that means we use this equation. We don't care about the time. V squared equals v0 squared plus 2a delta y. The reason why using that top part, because what's the velocity at that point? So this first term goes away. The v0 squared goes away. And so that means v is just the square root of 2 times a sub g times delta y, giving us 2 times 9.8 times 125 meters. Now, a little bit of a side here, guys. You heard me stressing about the directions, right? Okay. Now, as you can see, I didn't write that. So let's examine that a little bit. If the acceleration is downward and up is positive, the acceleration should be what? Positive or negative? Negative. If upward is positive and the object is falling or has gone down in height, is the change in height positive or negative? So therefore, this should be 2 times negative 9.8 meters per second squared times negative 125 meters. Good news, the 2 negatives will cancel and give us a positive, so we can take a square root. There's another way of doing this. We could say that down is positive. If down is positive, then both of those numbers would be positive, wouldn't they? And so we still end up getting the same result. The trick that we do have to watch out for, though, I can find the speed, but to find the velocity, I need to know the direction. The speed turns out to be 49.5 meters per second. But what's the direction, up or down? Downward. So if up is positive, then the velocity should be negative 49.5. Remember, when you take a square root, you've got 2 possible answers, a positive and a negative root. Look at your diagram to see which one applies. Everything make sense there, guys? Cool. Fantastic. Not hard, is it? It's a lot of steps. And that kind of gives you the example of what I was talking about. In the class, I give you the skills. It's similar to carpentry where I teach you how to saw or glue or hammer or drill. You get the skills, right? Then I give you the homework, which is essentially make a cabinet, right? You're going to use the skills, aren't you? The trick is, how do you use the skills? And I cannot tell you every way on how to use the skills. It's just one of those things that you have to do on your own over and over and learn as you go. That's why I give you the homework. Most of the problems are fairly straightforward, but some of the problems you got to build a cabinet, if you will. Okay? My own personal experience, you can learn by doing. I mean, after all, back to the cabinetry example, it took me 3 hours to hang a door on a closet one day. Now that sounds ridiculous, doesn't it? How hard could it be to hang a door on a closet? And the answer is, not hard, except I kept doing everything wrong. I kept making mistakes along the way. Putting the hinges in the wrong spots. Putting the door face backwards. Putting the door upside down. Putting the door with the handle next to the hinge. Okay? If there was a way to screw up hanging a door, I found it. Okay. Can't do that in an old house. So anyway, the end result was, when I finally got done, I finally got the door hung up. After I said a few words, I said, okay, now I know what I'm doing. And so the subsequent doors I hung up would take anywhere from 5 to 10 minutes each. Okay, so again, that's the reason why the homework gets somewhat complicated. I realize that there's an old meme out there. Class is add water and stir, right? And then homework is, here's a recipe for making a pie, make the pie. And then the test is, you're now a contestant on Chopped or something like that, right? You see where I'm going here? Okay, any questions for me? Then let's go ahead and call it a day, and I will see you guys all later.